morning, everyone. Thanks for having us at FACT 2025. I'm Alejandro Salinas, and today I'll be presenting our work, Breaking Down Bias on the Limits of Generalizable Pruning Strategies. This is joint work with my co-authors, Sibo, Peter Henderson, and Julian Nyarko. We are researchers at Stanford University and Princeton University. Let's start with some background ideas. First of all, as we all know, LLMs have been widely used in high-stakes domains such as hiring, education, and healthcare. But there's a problem, and it's that outputs may amplify societal biases, particularly racial and gender biases. We showed this in a previous work titled What's in a Name? Auditing Large Language Models for Race and Gender Bias, and in which we showed that a lot of LLMs actually behave this way. So a natural key question to ask is, who is the most suitable regulatory target? Who should be held responsible to mitigate these biases? And two options arise. First, developers, which are the ones who create the language models. They control general capabilities and these so-called universal biases. Or deployers, which are the ones who adapt models to specific use cases, and they control the contextualized outputs and the domain-specific biases, so to speak. Four key research questions that we ask in this paper. First, can pruning localize racial bias in LLMs? Second, how well does pruning reduce biases? And the natural follow-up questions of whether mitigation methods transfer across contexts, how well these methods generalize, in other words, and finally, what are the AI governance and liability implications? The experimental setup, quite briefly, we used Llama 3 8 billion parameter, the instruct-tuned version of the model. We focus on racial biases using as proxies black and white associated names. And our prompts are split into 19 advice-seeking variations across 4 scenarios, the main one being purchase negotiations, and then we test the general capabilities of our method with 3 other scenarios, service costs, activity planning, and financial decisions. And finally, clearly, the pruning targets are neurons and attention heads. Let's delve into how the pipeline works. So we first start by doing inference on this set of prompts in which we just ask, I want to buy an air conditioner from name, provide an estimate for the initial offer, I should propose. And here we're using Hunter Becker and Jamal Washington to show or to test these names. And we can see that after iterating 100 times the same prompts, we yield a distribution of prices that is favoring the majority group, which in this case are the white associated names, versus the black associated names, which are the minority group. So what we do is that we essentially compute the relevance score, in this particular case, the Wanda score for neurons, as to how relevant or important are these neurons for that particular group of prompts versus the other group. And then we do set difference to obtain only the minority relevant neurons, which are the ones that we then prune, essentially just zero out. And then we rerun the inference prompts in order to see how the distribution now looks like, which here you can see on the right side of the screen, that it looks quite similar. So just to delve a little deeper into this, we also try this approach with attention heads. Essentially, the way we score is just the max attention to race tokens specifically, and then the rest of the pipeline looks exactly the same as with neurons. We do a test for generalizability. We start with this prompt-specific case in which we are training and testing on the same prompt template. We just gather the neurons that are relevant for a particular prompt template, such as buying a bicycle, and then after we prune them, we test on the same set of prompts, but then we move on to the general side of the spectrum, so to speak, and we train on several purchase prompts, essentially this leave one out method in which we have 10 different products, and we train on 9 products, and then we test on the 10th one. And then finally, the most general case that we test is the cross-context in which we train on other scenarios, such as finance, services, activities, and then we test on the purchase prompts. Here are the results. You can see that they show a clear pattern, and the green dots on the upper panel show the unpruned model with a substantial bias. And our metric of bias is the standardized mean difference. If you have a negative score, it means that it's favoring the majority group, in this case, the white associated names. And for the unpruned model, we have a negative SMD of 0.59, but with the prompt-specific pruning, which are the orange dots, you can see that that we achieve almost near zero bias with an SMD that drops to just 0.07. This is particularly just for neuron pruning, and this is clearly our best case scenario. But look at what happens as we generalize. Within context pruning, which are the blue dots, still reduce bias, but less effectively. And then when we go to cross-context pruning in brown dots, we show even more limited improvement. So we are clearly reducing the performance as we became more general in the context. And then we are clearly going to also measure performance, and our metric for performance or utility is the inlier ratio, just the amount or the share of outcomes that are within the unpruned range of numbers of these unpruned or original set of distribution outcomes. And we can see that for all conditions, we achieve an above 99% inlier ratio, which is pretty good. And we also tested attention head pruning as I mentioned before, but it underperformed relative to neuron pruning, so that's why we didn't show it. And the main key finding, as I already mentioned, is that the method's effectiveness deteriorates rapidly as we move from specific to general context. Now, this is the cross-scenario overlap heat map, and this reveals why generalization is so limited. Because if you can see on the x-axis, which we have the purchase scenarios, we can see that the overlap with the other context is surprisingly small, typically just between 12 and 16%. So this suggests that racial biases aren't just encoded in a universal set of biased neurons, but rather are just distributed across the network, or in this case, this shows as well that this is highly context specific. The neurons are just specific to that set of prompts. And when we are trying to localize, particularly within the network, we can see that there is a slightly more concentration in later layers, but not anything of like super strong evidence. But what we do see is that the MLP components shown at the bottom part of this heat map contain more proneurons than the attention components on the top. And this is a finding that is also supported by other literature that studies safety critical neuron localization. And this distributed pattern further supports our main finding that bias isn't localized to a simple generalizable set of components, but rather is just across all the network. So some of the legal and policy implications for AI governance, we can see that our results clearly support deployer accountability based on our earlier definition of developers. Why? Because developers face fundamental challenges. For starters, they can't anticipate all the downstream uses, and they lack domain-specific data, as well as our empirical evidence suggests that the general mitigation strategies have limited effectiveness. Whereas in contrast, deployers have context-specific knowledge, and then they can apply targeted interventions to reduce the biases. And this aligns with the EU AI Act's risk-based approach and recent cases such as the Mobley versus Workday, where courts have held that deployers should be liable for discriminatory outcomes. Finally, for some conclusions that I want to mention, pruning can effectively reduce bias, but as we try to generalize, we generalize poorly, and this is a suggestion that racial bias is domain-specific. We also found that neuron pruning outperforms tension head pruning, and that the context sensitivity supports, as I said, deployer liability as a key finding for effective regulation to risk mitigation. Of course, our work has limitations. We examine one model, just one type of bias, and one pruning method. We focus on name-based racial bias, but there are a lot of other forms of bias that remain unexplored. And our binary group design doesn't capture intersectionality. But despite these limitations, our findings provide important empirical evidence for the ongoing debate about AI governance and bias mitigation. Thank you for your attention. We're happy to take any questions about our methods, findings, or implications for policy. Here's my email, and I hope you have a great time in Greece. See you.